The gold in your wedding ring was forged in a catastrophe. Since 2017, scientists had only one confirmed source for it: two dead stars colliding over millions of years. Then, in 2025, they confirmed a second, smaller, faster, and far stranger. A single dead star, barely 20 kilometers across, cracked open its own surface and built gold in the wreckage. The object is called a magnetar, the corpse of a massive star wrapped in the strongest magnetic field ever measured. When its crust fractures, it flings nuclear debris into space at 1/10 of the speed of light, and in that cooling cloud, the periodic table assembles itself in seconds. One such event produced roughly 1/3 of Earth's mass in heavy elements. It also warps atoms, splits light in two, and compressed our planet's magnetic field from 50,000 light-years away. If you want to know how a dead star builds gold from its own wounds, hit that like button and subscribe. Now, let's begin. The morning of December 27th, 2004, was quiet across most of the world. Christmas had just passed. Offices were closed. Families were still working through leftovers and wrapping paper. Observatories across 3 continents ran on skeleton crews. Across the Northern Hemisphere, the lull had settled into everything, including the monitoring stations that keep continuous watch on the high-energy sky. Gamma-ray satellites orbited in their pre-programmed routines, sweeping through wavelengths and energy bands, recording the usual low-level hum of cosmic background radiation. Nothing remarkable was expected. No solar flare warnings had been issued. No unusual activity had been flagged in any of the weekly source catalogues. It was the kind of day where the universe seemed, for once, politely uneventful. But 50,000 light-years away, at the far end of a journey that had begun before modern humans existed, a wave front of gamma radiation was converging on the solar system. It had been travelling through the galaxy since before the last ice age, before agriculture, before language. The light had left its source when woolly mammoths still walked the Earth, and it had crossed the entire breadth of the Milky Way in total silence. The event that produced it had already happened. A dead star, a stellar remnant roughly 20 kilometers across, had fractured its own surface and released more energy in a fraction of a second than most stars produce in hundreds of thousands of years. That energy was now arriving at Earth, and nothing in the solar system was ready for it. At 21 hours 30 minutes and 26 seconds universal time, the wavefront hit. The first instrument to register the blast was the RESI satellite, a NASA observatory designed to study solar flares. It was not even pointing at the correct part of the sky. That detail did not matter. The gamma-ray flux was so overwhelmingly intense that it flooded the detector sideways, saturating the instrument's electronics from an angle it was never designed to receive. Within the same fraction of a second, the European Space Agency's Integral Gamma-Ray Observatory recorded a surge so far beyond its calibrated range that the data went off scale. The detector did not merely peak, it flatlined at its maximum output and stayed there, blinded by a wall of radiation arriving from deep within the galactic plane. Then the cascade spread across the solar system. Satellite after satellite, probe after probe, instrument after instrument reported the same impossible signal arriving from the same direction in the sky. The swift gamma-ray observatory registered the burst. The WIND spacecraft, orbiting far from Earth at the first Lagrange point, a gravitational balance point roughly 1.5 million kilometers sunward, picked it up clearly. Ulysses, a solar observation mission traveling on a distant elliptical orbit around the Sun far from any planet, detected the event from the opposite side of the solar system. The Mars Odyssey probe, circling Mars at the time of the burst, caught the flash. The Cassini spacecraft, stationed near Saturn more than 1 billion kilometers from Earth, recorded the gamma-ray pulse across that enormous distance. Even the GEO-tail satellite, an instrument built specifically to study the physics of Earth's magnetic tail rather than distant astrophysical sources, registered the arrival of the wavefront. In total, more than a dozen separate instruments spread across the entire solar system were simultaneously struck by the same burst of gamma radiation, and every single detector that was capable of being saturated was saturated. Some instruments took minutes to recover, Others produced corrupted data that required weeks of reconstruction. No one had ever seen a single astrophysical event simultaneously overwhelm that many spacecraft at once. The energy was not supposed to be possible from any known compact object, but the instruments were only the beginning of the story. The gamma-ray wavefront did not just register on sensors, it physically struck the Earth. When the leading edge of the burst arrived at our planet, it slammed into the magnetosphere, the magnetic bubble generated by Earth's liquid iron core that shields us from charged particles and solar wind. The impact was not subtle. Magnetometers on the ground detected a sudden compression of the dayside magnetosphere. The ionosphere, the electrically charged upper layer of our atmosphere that enables long-range radio communication, responded almost instantly. The burst ionized the night side of Earth's upper atmosphere to a depth and intensity normally associated with powerful solar flares. Radio propagation was disrupted. The electrical conductivity of the upper atmosphere spiked measurably. For a brief window of time, a dead star 50,000 light-years away was altering the electrical properties of our planet more aggressively than the Sun does during a moderate geomagnetic storm. Hold that comparison in your mind for a moment, because it contains the seed of everything that makes magnetars terrifying. The Sun is roughly 8 light minutes from Earth. It is our star. It dominates our sky, drives our weather, sustains every ecosystem on the planet. When the Sun produces a major flare, the effects on Earth can be catastrophic by human standards. Geomagnetic storms knock out power grids. Satellites lose orientation. We treat solar flares as serious natural hazards, and rightly so. The Sun is close, enormous, and actively burning nuclear fuel at a furious rate. Now consider that SGR 1806-20 is not 8 light minutes away. It is 50,000 light-years away. That distance is so vast that the photons arriving in December 2004 had been travelling since before Homo sapiens first walked upright. The magnetar is not 1,000,000 miles across. It is roughly 12 miles across, smaller than many metropolitan areas. It has no nuclear fusion, no sustained energy source in the traditional sense. It is a dead stellar remnant. And from 50,000 light-years, it still compressed our magnetic field, ionized our atmosphere, and disrupted radio propagation on the night side of Earth. The sheer violence required to produce a detectable physical effect at that range, from an object that small, is almost impossible to emotionally process. But the instruments recorded it. The data is unambiguous. It happened. The source was a magnetar designated SGR 1806-20. The name derives from its classification as a soft gamma repeater, a category of object known to emit irregular, repeating bursts of relatively low-energy gamma radiation. The numbers in its designation encode its approximate coordinates on the celestial sphere, but there was nothing soft about the December 2004 event. This was the most powerful burst ever recorded from any magnetar in observational history. Scientists classify it as a giant flare, a rare and extreme category of magnetar outburst, and the December 2004 event from SGR 1806-20 was roughly 100 times more energetic than the only 2 giant flares that had ever been observed before from other magnetars. It did not just set a record, it obliterated the previous scale. The energy numbers are where human intuition begins to collapse entirely. In the initial spike of the flare, lasting approximately 0.2 of a second, the magnetar released energy equivalent to roughly 10 to the 46th ergs. That scientific notation is convenient for physicists, but meaningless for everyone else. So let me translate it into terms that might land somewhere in your brain, even if your brain immediately rejects them. Our Sun is a nuclear furnace nearly 1,000,000 miles across. Every second, it converts approximately 4 million tons of hydrogen into helium through nuclear fusion, releasing energy at a rate of roughly 4 times 10 to the 33 ergs per second. The Sun has been doing this for 4.5 billion years and will continue for another 5 billion. It is a staggeringly powerful object by any terrestrial standard. Now, take all the energy the Sun produces in a single year, multiply that by 250,000, stack 250,000 years of continuous solar output into one figure. That is approximately what SGR 1806-20 released in less time than it takes you to blink, 1/5 of a second. 250,000 years of solar energy from a dead object roughly the diameter of a mid-sized city. There is no framework within everyday human experience that can absorb this comparison. The numbers are correct, confirmed independently by multiple research groups analyzing data from multiple spacecraft. But they feel wrong. They feel like an error. They are not. The universe is simply capable of concentrating violence into packages so small and so intense that the result defies every intuitive expectation about the relationship between size and power. The flare was so luminous that if it had occurred not in our galaxy but in the Andromeda galaxy, 2.5 million light-years away, ground-based gamma-ray detectors on Earth would still have registered the signal. Not a space telescope operating at the bleeding edge of sensitivity. Ground-based instruments. A magnetar flare bright enough to be observed from an entirely different galaxy, across a void of intergalactic space that contains almost nothing. That detection range puts the December 2004 event in a category of astrophysical violence that overlaps with the most energetic explosions in the known universe. For a fraction of a second, a single neutron star remnant produced a burst so intense that it briefly approached the luminosity territory of cosmological gamma-ray bursts, events associated with the deaths of the most massive stars or the collisions of entire compact objects. But here is where the magnetar story diverges from every other violent phenomenon you have ever heard about in astrophysics. And this divergence is the key to understanding why magnetars deserve the title of most violent objects in the universe. Supernovae are violent. They are the explosive deaths of massive stars, releasing the gravitational binding energy of a collapsing stellar core in a blast that can briefly outshine an entire galaxy. But a supernova happens once. The star dies, the explosion fades. What remains is a remnant, a neutron star or a black hole, sitting quietly in the debris. The violence is terminal. It marks an ending. Black hole mergers are violent. Two of the most extreme gravitational objects in the universe spiral toward each other over millions of years, accelerating to significant fractions of the speed of light before colliding and fusing into a single, larger black hole. The merger produces gravitational waves powerful enough to be detected billions of light-years away. But the event happens once. The two black holes become one. The violence is the collision itself, and when it ends, a single quiet black hole remains. Gamma-ray bursts are violent. They represent either the birth scream of a new black hole formed in a collapsing star or the catastrophic merger of two neutron stars. They are the brightest electromagnetic events in the universe, visible across billions of light-years. But again, they are singular events. The burst fires, the afterglow fades, the source either becomes a black hole or is destroyed entirely. Nothing repeats. Magnetars are fundamentally different. They flare, they recover, they flare again. The violence is not a single terminal event. It is a recurring condition. SGR 1806-20 did not destroy itself in December 2004. The crust fractured, the magnetic field reconfigured, a relativistic fireball erupted into space, and then the magnetar continued to exist. Within hours, instruments detected the familiar pulsation of its 7.56-second spin period, ticking away with clockwork regularity, as though the most energetic outburst in recorded magnetar history had been nothing more than a particularly bad day. The object was still there, battered, restructured, magnetically rearranged, but intact and operational, ready to build stress again, ready to fracture again, ready to do all of it again. This is the distinction that separates magnetars from every other violent phenomenon in the cosmos. Their violence is not the violence of death, it is the violence of ongoing existence. They are objects that live in a state of perpetual physical extremity, where the baseline conditions on and around the star are so far beyond anything else in the known universe that periodic catastrophic energy releases are simply part of what it means to be a magnetar. The giant flares are not malfunctions, they are not anomalies, they are features of the system. The star builds stress, the stress exceeds the breaking point, the crust fractures, energy erupts, the star settles, the cycle begins again, Consider what is actually happening inside the star during one of these events. The magnetic field of a magnetar is not a passive feature hanging in space around the neutron star like some invisible cloud. It is physically embedded in the star's crust, threaded through the crystalline lattice of exotic nuclear material that makes up the outermost solid layer of the neutron star. That crust is extraordinary material. It is not rock. It is not metal in any conventional sense. It is a rigid lattice of neutron-rich atomic nuclei, packed so densely that a volume the size of a sugar cube would weigh roughly 1 billion tons on Earth, comparable to the mass of a small mountain compressed into a space you could hold between two fingers. This material is harder and more rigid than anything else in the observable universe. Diamond is soft by comparison. Steel is tissue paper. The neutron star crust is the ultimate solid, forged under pressures that do not exist anywhere else in nature, and the magnetic field is strong enough to break it. As the magnetar's internal field evolves over time, twisting and reconfiguring through processes deep within the neutron-rich superfluid core, the crust comes under increasing mechanical stress. Magnetic pressure builds against the rigid lattice from below, loading it with forces that grow stronger week after week, month after month, sometimes for years. And then, when the accumulated magnetic force exceeds what even this impossibly rigid material can withstand, the crust fractures. A starquake, the neutron star equivalent of an earthquake, except that the energy scales are not remotely comparable. When the crust of a magnetar slips by even a single millimeter, the energy released is sufficient to vaporize hundreds of trillions of metric tons of surface material instantly. That tiny displacement, 1 millimeter on a star 12 miles across, triggers temperatures high enough to annihilate matter at the fracture site. The crack then shakes the magnetic field with such ferocity that the field lines snap and reconnect in a catastrophic global reconfiguration, converting enormous reserves of stored magnetic energy into a fireball of superheated plasma. Photons and electron-positron pairs erupt outward at velocities approaching the speed of light. That is the giant flare. That is what crossed 50,000 light-years and still compressed Earth's magnetosphere, a millimeter on a dead star. 50,000 light-years away, and you felt it. The December 2004 flare was not the first giant flare ever detected from a magnetar, but it stood so far above the others that it essentially defined a new tier of astrophysical violence. The first recorded giant flare arrived on March 5, 1979, from a magnetar called SGR 0526-66, located not even in our own galaxy but in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of roughly 160,000 light-years. That event baffled scientists profoundly because no known mechanism at the time could explain such an intense gamma-ray burst from a compact stellar source. Neutron stars were understood to exist. Pulsars had been discovered a decade earlier, but nothing in the established physics of neutron stars predicted that one could produce this kind of energy release. The event was so anomalous that it lingered in the scientific literature for years as an unexplained puzzle. The theoretical framework needed to account for it would not arrive for another 13 years, when Robert Duncan and Christopher Thompson proposed the magnetar model in 1992. The second giant flare came on August 27, 1998, from SGR 1900+14, a magnetar roughly 20,000 light-years from Earth. That burst was powerful enough to measurably ionize Earth's upper atmosphere and cause detectable disturbances in radio wave propagation. It provided the first strong observational confirmation that the magnetar model was real, that neutron stars with extreme magnetic fields could produce the kind of energy output that Duncan and Thompson had predicted. But the 2004 event from SGR 1806-20 surpassed the previous two flares by a factor of 100. Not twice as powerful, not 5 times, 100 times. It took everything scientists had learned from the first two events and rendered those events footnotes by comparison. 3 giant flares across 25 years, each from a different magnetar, each demonstrating energy releases that should not be physically possible from objects this small. And the final one in the sequence dwarfed the previous two so completely that theorists were forced to reconsider not just the upper limits of what magnetars can do, but whether existing models captured the full scope of magnetar violence at all. But the December 2004 flare carried a secret that scientists did not uncover for another 20 years. In 2025, a team of researchers led by Anirudh Patel published a landmark paper in the astrophysical journal Letters that changed how physicists think about the consequences of magnetar violence. They presented direct evidence that the giant flare from SGR 1806-20 had not merely released energy into the surrounding space, it had forged new elements. The analysis demonstrated that material blasted from the magnetar's fractured crust, ejected outward at roughly 10% the speed of light, had undergone rapid neutron capture, a nuclear process known as the R process. This is the same mechanism that physicists believe produces heavy elements like gold, platinum, and uranium inside the catastrophic debris of colliding neutron stars. The team showed that the delayed gamma-ray emission detected for hours after the initial flare spike, an emission component that had puzzled researchers for 2 decades and remained largely unexplained in the literature, matched the predicted radioactive decay signature of freshly synthesized R-process nuclei with striking precision. The light curve shape, the total emitted energy, the spectral distribution of the gamma-ray photons, all of it aligned with what nuclear physics predicts should happen when freshly assembled heavy nuclei begin to radioactively decay in an expanding cloud of debris. Magnetars were not just releasing energy, they were manufacturing atoms that had never existed before. The violence was not purely destructive, it was simultaneously creative, building new elements in the same cataclysmic event that shattered the star's surface and launched a relativistic fireball into the cosmos. In the same fraction of a second that produced temperatures high enough to annihilate matter, the expanding debris was cooling and assembling heavy nuclei through a cascade of neutron captures that climbed the periodic table in real time. That discovery made magnetar giant flares only the second confirmed astrophysical site of R-process nucleosynthesis in the universe. After the neutron star merger detected through gravitational waves in 2017, the implications are staggering and reach directly into your daily life. It means that some fraction of the heavy elements present in our galaxy, the gold in your jewelry and electronics, the platinum in industrial catalysts and medical equipment, the uranium that powers nuclear reactors, may trace its origin not to the collision of 2 dead stars spiraling together over millions of years, but to the self-inflicted wounds of a single one. A magnetar cracked its own surface open, and in the expanding debris of that crack, the universe built gold. And here is what makes the magnetar phenomenon so deeply disorienting compared to anything else in astrophysics. We are not looking at an explosion that happens once, scatters debris, and fades into history. We are looking at an object that periodically shatters its own surface, launches material at relativistic speeds, forges new elements in the expanding wreckage, and then reassembles itself to begin the cycle again. Giant flares are the most dramatic and energetic expression of this behavior, but they represent only the peak of a much broader and more persistent pattern of violence. Magnetars, classified as soft gamma repeaters, earn that classification precisely because they repeatedly emit bursts of gamma radiation at irregular intervals throughout their active lifetimes. Some magnetars enter furiously active phases lasting weeks or months, producing hundreds or even thousands of individual bursts in rapid succession. Others remain eerily quiet for years at a stretch before erupting without any detectable precursor or warning. The giant flares are the headlines that make the news. The routine bursts are the daily weather of a magnetar's existence, and both emerge from the same underlying engine, a magnetic field so powerful that it is slowly, perpetually, relentlessly rearranging the physical structure of the star from the inside out. Only about 30 magnetars have been confirmed in the Milky Way, 30 objects out of the estimated hundreds of millions of neutron stars that populate our galaxy. They are phenomenally rare. Their active lifetimes are short by cosmic standards, roughly 10,000 years before the magnetic field decays enough that the extreme behavior subsides and the magnetar settles into a quieter existence as an ordinary neutron star. 10,000 years is nothing on astronomical timescales. It is less than the blink of an eye compared to the age of the galaxy. Yet during that brief window of activity, these objects produce effects that are detectable from other galaxies entirely. A single magnetar, 12 miles wide, can briefly outshine every other source of gamma radiation in the Milky Way. It can ionize the atmosphere of a planet on the other side of the galaxy. It can forge heavy elements in its own debris. It can produce signals that would be measurable from the Andromeda galaxy. The ratio between the physical size of the object and the scale of its consequences is perhaps the most deeply unsettling feature of the entire phenomenon. The object is smaller than most metropolitan areas, smaller than the island of Manhattan. You could drive across it in 20 minutes at highway speed. And its violence reaches across distances measured in tens of thousands of light years. Nothing else in the universe concentrates so much physical hostility into so little space. When scientists describe magnetars as the most violent objects in the universe, they are not using that word loosely or reaching for dramatic effect. They are describing a measured, confirmed, independently verified physical reality. The energy density per unit mass during a giant flare, the rate of energy release per unit time during the initial spike, the mechanical forces required to fracture the hardest material known to exist, the magnetic field strengths that exceed anything else observed anywhere in the cosmos by factors of thousands. All of these quantities simultaneously occupy the extreme upper boundary of what is physically achievable by matter in our universe. Black holes are more massive. Supernovae release more total energy, integrated over their full multi-week duration. Sustained gamma-ray bursts are brighter, when averaged over several seconds, but nothing in the known universe combines this many forms of physical extremity into a single object this small. Magnetars are simultaneously the strongest permanent magnets ever measured, the densest confirmed stable matter, the most energetic per unit mass transient emitters, and the most mechanically violent solid objects ever observed. Every superlative applies at once, stacked on top of each other, and they all apply to a dead star that you could walk across in an afternoon. The question that drives the rest of this story forward is not whether magnetars are extreme. The instruments settled that question 2 decades ago with data that no one has been able to dispute. The question is how. How does a dying star produce something this hostile? How does a magnetic field reach strengths that physically distort the shape of individual atoms? How does a dead remnant with no nuclear fuel, no active fusion, and no conventional energy source manage to outperform living stars by factors so large they overwhelm standard scientific notation? The answer begins with the collapse itself, with the precise moment when a massive star exhausts its fuel and its iron core compresses under its own weight into something so dense, so extreme, and so fundamentally alien to the rules of normal physics that the universe has no gentle category left to place it in. What comes next is the story of that collapse, the forces it unleashes, and the impossible object it leaves behind. Every magnetar begins as something beautiful, a massive star, burning with the kind of luminosity that makes our sun look like a candle flame next to a searchlight. Stars destined to become magnetars are not average. They are the largest, rarest, most luminous stars in the galaxy. Objects carrying 8, 10, 20, sometimes 25 or more times the mass of our sun, blazing through their nuclear fuel with a ferocity that guarantees a short and spectacular life. While a star like ours will burn steadily for roughly 10 billion years, these massive stars exhaust themselves in just a few million. They are born in violence inside collapsing molecular clouds. They live fast, and they die in the most energetically extreme events the universe routinely produces. What makes the magnetar story so disorienting is that the death of these stars is not the end of the violence. It is the beginning. To understand how a magnetar forms, you need to understand what happens inside a massive star during the final hours of its life. And those hours are among the strangest in all of astrophysics. A star is a balancing act. Gravity pulls inward, trying to crush the star into the smallest possible volume. Nuclear fusion pushes outward, generating pressure from the energy released as lighter elements fuse into heavier ones. For most of a star's life, these two forces are in equilibrium. Gravity squeezes, fusion pushes back. The star holds its shape, but this balance depends entirely on the star having fuel to burn. In its core, a massive star fuses hydrogen into helium for millions of years. That initial fuel supply seems abundant, but massive stars burn it with reckless intensity. radiating energy at rates thousands of times greater than our Sun. When the hydrogen in the core is finally exhausted, gravity gains a temporary advantage and the core contracts, the temperature and pressure rise, and then helium begins fusing into carbon and oxygen. Equilibrium is restored, but at a higher temperature, a higher pressure, and a faster burning rate. When the helium is exhausted, the cycle repeats with each new fuel source. Carbon fuses into neon and magnesium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. Each successive stage requires higher temperatures and pressures than the last. Each stage burns through its available fuel faster than the one before it. The acceleration is staggering. Hydrogen fusion lasted millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts a few hundred years. Neon burning lasts roughly a single year. Oxygen burning lasts a few months, and then comes silicon. Silicon fusion is the final act, and it unfolds with terrifying speed. The core temperature has now reached roughly 3 billion degrees. Silicon nuclei fuse into iron and nickel group elements through a blizzard of nuclear reactions that consume the remaining fuel in approximately 1 day. A single day. After millions of years of steady hydrogen burning, the star reaches its final fuel source and exhausts it before the planet. It illuminates, completes a single rotation. During those final hours, the star appears completely normal from the outside. Its surface glows. Its outer layers remain stable. To any observer, the star looks unchanged, but inside a catastrophe is assembling itself. Iron is where everything stops. Every fusion reaction before iron released energy. That released energy was what generated the outward pressure that held the star up against gravitational collapse. But iron sits at the bottom of the nuclear binding energy curve. Fusing iron does not release energy. It consumes energy. It is an endothermic reaction. The moment a massive star accumulates an iron core, it has built its own death sentence. The core is generating no outward pressure. It is simply sitting there, growing heavier and hotter, supported only by a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being squeezed together beyond a certain density. This is the last line of defense, and it has a limit. That limit is called the Chandrasekhar mass, named after the physicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. When the iron core exceeds approximately 1.4 times the mass of our Sun, electron degeneracy pressure can no longer support it. The electrons, despite their quantum mechanical resistance, are forced to combine with protons in a process called neutronization. Protons and electrons merge to form neutrons and neutrinos. The neutrinos escape, the electrons vanish, and with them goes the last force holding the core up against gravity. What happens next takes less than a second. And it is among the most violent processes in all of nature. The core collapses, not slowly, not gradually, not with any warning visible from the surface, in free fall. The inner core, roughly the mass of our Sun packed into a volume roughly the size of the Earth, plummets inward at speeds reaching 70,000 kilometers per second, approximately a quarter of the speed of light. The density doubles, then doubles again, then again. In approximately 10 milliseconds, the core compresses from a sphere thousands of kilometers across to a ball roughly 20 kilometers in diameter. The atoms that made up the core have been destroyed. Electrons have been forced into protons. The protons have become neutrons. An entire stellar core has been converted from a mix of iron nuclei and electrons into a sea of nearly pure neutron matter in less time than it takes a hummingbird to beat its wings once. The collapse is so fast and so localized that the outer layers of the star do not even know it has happened. Information about the core's destruction cannot travel outward faster than the speed of light, and the collapse completes before the signal can reach the surface. For a fraction of a second, the outer 90% of the star sits peacefully in place, radiating light as though nothing is wrong, while beneath it, the core has already transformed into one of the most extreme objects the universe can produce. The star is dead from the inside out. Its surface just has not received the news yet. As the collapsing material reaches nuclear densities, roughly 230 million metric tons per cubic centimeter, a density so extreme that a single teaspoon of the material would outweigh every building in New York City combined. A new force activates. The strong nuclear force, which normally operates only over subatomic distances and binds protons and neutrons together inside ordinary atomic nuclei, becomes repulsive at the incredibly short ranges now being achieved as neutrons are packed essentially on top of each other. The core stiffens violently. The material that was in freefall an instant ago suddenly encounters a wall of nuclear repulsion so rigid that it might as well be hitting solid diamond at a quarter of the speed of light. The infalling material rebounds. It bounces. That bounce sends a powerful shockwave outward through the still collapsing outer core, a wave of compressed matter and energy travelling at tens of thousands of kilometers per second. The shockwave alone is not quite enough. It loses energy as it plows through the dense infalling material above the core, and it would stall before reaching the surface if not for a critical boost. The collapsing core releases an almost inconceivable flood of neutrinos during the neutronization process. Roughly 99% of the total gravitational energy released by the collapse, roughly 3 times 10 to the 46 joules, is carried away by neutrinos in the first few seconds. Neutrinos interact with matter only weakly, but at the extreme densities near the core, even a tiny fraction of that neutrino energy is absorbed by the stalling shockwave, reviving it and driving it outward with enough force to tear the rest of the star apart. The outer layers of the star, everything except the newly formed neutron core, are ejected into space at speeds of thousands to tens of thousands of kilometers per second. This is the supernova, the most energetic routine explosion the universe produces. It can briefly outshine the combined light of every other star in its host galaxy. And the compact remnant left behind at the center, the newly born neutron star, now begins its existence as one of the most extreme objects in nature. And this is where you need to recalibrate your sense of what matter can be. A neutron star contains roughly 1.4 to 2 times the mass of our Sun, compressed into a sphere approximately 20 kilometers across. To grasp how extreme that density is, consider this. Every human being who has ever lived on Earth, all of the roughly 100 billion people who have been born across the entire history of our species, if you could somehow compress every single one of them together into neutron star material, the result would fit inside a volume roughly the size of a large grape. That is not an exaggeration. It is arithmetic. Neutron star matter is so dense that conventional descriptions of solids, liquids, and gases cease to apply. The material at the surface forms a crystalline lattice of neutron-rich nuclei, unlike anything found elsewhere in nature. Deeper inside, the matter transitions into a neutron superfluid, a quantum liquid with zero viscosity that flows without resistance. At the very center, conditions may become so extreme that neutrons themselves dissolve into their constituent quarks, forming a quark plasma that has not existed freely since the first microseconds after the Big Bang. The gravitational field at the surface of a neutron star is roughly 200 billion times stronger than Earth's surface gravity. If you could somehow stand on a neutron star, which you cannot because you would be crushed into a layer of atoms thinner than a coat of paint, you would weigh roughly 200 billion times your Earth weight. A baseball placed on the surface would weigh more than the Great Pyramid of Giza. Light leaving the surface is measurably bent by the gravitational field, curved so strongly that you could see parts of the back of the star while looking at the front. The escape velocity is roughly 150,000 kilometers per second, approaching half the speed of light. These are confirmed physical properties derived from the measured masses and radii of observed neutron stars, cross-checked against predictions from general relativity. Most neutron stars become pulsars. The reason is angular momentum conservation, one of the most fundamental laws in physics. The collapsing core retains all of the rotational momentum it possessed before the collapse, but the radius shrinks by a factor of tens of thousands. The same principle that makes an ice skater spin faster when she draws her arms tightly against her body applies here, but magnified to cosmic proportions. A star that rotated once every few weeks before its core collapsed becomes a neutron star spinning multiple times per second after the collapse completes. Some newborn neutron stars rotate at truly extraordinary rates, hundreds of revolutions per second, their surfaces moving at a significant fraction of the speed of light. These rapidly spinning objects carry magnetic fields inherited from the parent star, amplified by the compression. A typical stellar magnetic field of a few Gauss becomes, after the collapse compresses it into a tiny volume, a neutron star field of roughly 100 million to 1 trillion Gauss. These are already enormous magnetic fields by any standard, millions of times stronger than the most powerful magnets humans have ever built. The spinning magnetic field sweeps beams of radio waves and X-rays across space like a lighthouse beam. When those beams happen to cross Earth's line of sight, we detect regular pulses, that is a pulsar. Jocelyn Bell Burnell detected the first pulsar in 1967, and for a brief moment, the regular pulses were so unexpected that the signal was half-jokingly labelled LGM1 for Little Green Men, before the true explanation emerged. Pulsars are extreme objects by any reasonable standard. They are dense beyond comprehension, spinning at rates that would tear any normal object apart, and magnetically powerful enough to make the strongest human-made magnets look negligible. But compared to magnetars, pulsars are the calm version of a neutron star, the domesticated version. The version that, while shocking when first discovered, eventually settled within existing theoretical frameworks. Magnetars shatter those frameworks completely. The question that consumed theorists for decades was deceptively straightforward. If all neutron stars form through the same basic core collapse mechanism, through the same gravitational implosion of an iron core, and the same bounce and supernova explosion, why do some end up carrying magnetic fields 1,000 times stronger than the rest? A typical pulsar carries a surface field of roughly 100 million to 1 trillion Gauss. A magnetar carries a surface field of 100 trillion to 1 quadrillion Gauss, with interior fields potentially even stronger. The jump is not incremental. It is not a modest variation within a normal distribution. It is a leap of 3 full orders of magnitude, a factor of 1,000. Something fundamentally different must happen during the formation of a magnetar to produce that scale of amplification. Simple conservation of magnetic flux during the collapse, the straightforward mechanism that gives ordinary pulsars their already impressive fields, cannot account for magnetar strength fields on its own. The arithmetic does not work. You would need the parent star to carry an impossibly strong magnetic field before the collapse, far stronger than any magnetic field ever observed in any star, for flux conservation alone to reach magnetar levels. Something additional must be happening in those first violent seconds. In 1992, Robert Duncan and Christopher Thompson proposed the answer. Their model, published in a paper that would eventually reshape an entire subfield of astrophysics, described a dynamo mechanism that operates during the first 10 to 20 seconds of a neutron star's life. The idea is elegant and physically violent. When the neutron star first forms, it is extraordinarily hot, with core temperatures exceeding 100 billion degrees. At these temperatures, the interior is not yet a superfluid. It is a turbulently convecting fluid of neutrons and protons, churning with ferocious energy as the newborn star radiates neutrinos and cools. If the neutron star is also spinning rapidly, rotating many hundreds of times per second in those first critical moments, the combination of rapid rotation and vigorous convection creates conditions for an extremely efficient dynamo. A dynamo converts kinetic energy into magnetic energy. Earth has one. The liquid iron outer core of our planet churns and circulates, and the combination of that convection with Earth's rotation generates our planetary magnetic field. The same basic physics applies to a newborn neutron star, but amplified to an almost unimaginable degree. The convective motions inside a newly formed neutron star are far more violent than anything in Earth's core. The rotation is thousands of times faster. The fluid is 1 billion times denser. Duncan and Thompson calculated that under these conditions, the dynamo could amplify the magnetic field from the already substantial post-collapse value to magnetar strength levels, 100 trillion Gauss and above, in a matter of seconds. The dynamo feeds on the neutron star's rotational energy and thermal energy simultaneously, converting both into magnetic field strength during that brief, ferocious window when conditions are right. The key requirement is spin. The neutron star must be rotating at or near millisecond periods, spinning roughly 1,000 times per second for the dynamo to reach its full efficiency. Not every collapsing core achieves this rotation rate. The spin depends on the angular momentum of the original stellar core, which varies from star to star based on mass, evolutionary history, and interactions with companion stars. Duncan and Thompson estimated that roughly 1 in 10 core collapse supernovae produces conditions favorable for the magnetar dynamo. The rest produce ordinary neutron stars or pulsars with standard strength magnetic fields. That 1 in 10 estimate has held up remarkably well against subsequent observations. Approximately 30 confirmed magnetars exist in a galaxy estimated to contain hundreds of millions of neutron stars, and the ratio, after accounting for the short active lifetimes of magnetars and the detection biases of our instruments, is consistent with roughly 10% of all neutron stars being born as magnetars. The Duncan-Thompson model was revolutionary, but it left certain questions unanswered. In particular, some observed neutron stars appeared to exhibit magnetar-like behavior, including bursts and outbursts characteristic of extreme magnetic fields, while carrying surface field measurements well below the traditional magnetar threshold. These objects, sometimes called low-field magnetars, seem to contradict the simple picture of a single dynamo mechanism producing uniformly extreme fields. If the dynamo was the whole story, how could an object behave like a magnetar without carrying a magnetar-strength external field? In February 2025, a team led by Andrei Igoshev published a paper in Nature Astronomy that offered a compelling resolution. They identified a mechanism called the Taylor-Sprout dynamo, which operates not during the initial convective phase but later, when material from the supernova explosion falls back onto the newly formed neutron star. This fallback material carries angular momentum that spins up the outer layers of the star, creating differential rotation between the crust and the interior. That differential rotation drives a secondary dynamo process that generates strong magnetic fields, but fields that may remain largely internal, buried beneath the surface rather than manifesting as the extreme exterior fields seen in classical magnetars. The result is a neutron star that looks magnetically modest from the outside, but harbours intense interior fields capable of producing magnetar-like bursts and activity. The Taylor-Sprout mechanism effectively expanded the magnetar family, showing that the standard Duncan-Thompson picture was not wrong but incomplete. Magnetars may form through multiple pathways, each producing objects with different exterior signatures but sharing the same fundamental trait: magnetic fields of extraordinary internal intensity that drive violent behavior. For decades, the formation of magnetars remained entirely theoretical. Scientists could observe magnetars after they had formed, could measure their spin rates and field strengths and burst properties, but no one had ever watched one being born. The supernova explosion that creates a neutron star is so bright and so chaotic that identifying the specific moment a magnetar ignites inside the debris seemed observationally impossible. The newborn neutron star is buried inside an expanding cloud of supernova ejecta, hidden from view behind layers of hot, opaque gas that take weeks or months to thin out. By the time the remnant becomes visible, the dramatic formation process is long over. Then, in December 2024, astronomers got lucky, and the universe cooperated. A star roughly 25 times the mass of our Sun, located approximately 1 billion light-years from Earth, exploded. The supernova was designated Supernova 2024, A4V, and it was immediately recognized as a superluminous supernova, at least 10 times brighter than a typical core collapse explosion. These extraordinarily luminous supernovae had long been suspected of harboring magnetar engines at their centers, newly born magnetars spinning so rapidly that they poured their rotational energy into the expanding debris, inflating the light output far beyond what the explosion alone could produce. The theoretical prediction was elegant. A magnetar born spinning at millisecond periods would carry an immense reservoir of rotational kinetic energy, and as the spinning magnetic field interacted with the surrounding debris, that energy would be converted into radiation over weeks and months. But this hypothesis had never been directly confirmed through a clear observational signature uniquely tied to a magnetar. Supernova 2024, AFAV, changed that in a way nobody expected. An international team of researchers, led by Joseph Farah and using the Las Cumbres Observatory's global network of 27 telescopes, monitored the supernova continuously for more than 200 days. What they found in the light curve was unprecedented. The brightness of the supernova did not just rise and fall smoothly, it pulsed. The light curve contained a rhythmic oscillation, a periodic brightening and dimming that accelerated over time. The pulses started slow and grew faster, producing a pattern that the researchers described as a chirp, the same term used to describe the accelerating signal of merging black holes detected through gravitational waves. The team identified the cause. Inside the expanding debris cloud, a newly formed magnetar was spinning rapidly and surrounded by a disk of fallback material. That disk was precessing, wobbling like a spinning top due to a relativistic effect called Lentz-Thirring precession, a prediction of Einstein's general relativity in which a spinning massive object drags the fabric of space-time around with it, causing nearby orbiting material to tilt and wobble. As the disk precessed, it periodically blocked and reflected light from the central magnetar, creating the rhythmic pulses visible in the light curve. As the disk gradually spiraled inward toward the magnetar, the precession rate increased and the pulses accelerated. The chirp was the signature of a magnetar, reshaping its immediate environment through relativistic frame dragging in the first weeks of its existence. The paper was published in Nature in March 2026. It represented the first direct observational evidence of a magnetar being born, not inferred, not modelled, observed. The chirp in the light curve was a fingerprint that no other known mechanism could reproduce. The team tested multiple alternative explanations and ruled them out one by one. Only the Lentz-Thirring precession of a disk around a newly formed magnetar matched the period, the acceleration rate, and the energy budget of the observed signal. For the first time, scientists had watched the birth of one of the most extreme objects in the universe. They had seen the moment when a dying star's core crossed the threshold from ordinary collapse into something far more hostile. The data confirmed what decades of theory had predicted. Magnetars are born in the hearts of the most powerful supernovae. They emerge spinning at extraordinary rates, carrying magnetic fields that immediately begin reshaping the matter and space-time around them. They are not quiet remnants left behind after the fireworks end. They are active participants in the explosion itself, pumping energy into the debris, warping the geometry of their surroundings, and establishing themselves as engines of violence from the very first seconds of their existence. And yet, the formation story, as dramatic and violent as it is, only sets the stage for what comes next. A magnetar, at the moment of its birth, carries a magnetic field of extraordinary strength. But the question that haunts physicists is not simply how the field got that strong. The question is what a field that strong actually does. Why does it translate into the kind of structural, radiative, and environmental violence we have already seen? Why does it make a magnetar fundamentally different from any other object in the universe, including the already extreme neutron stars and pulsars that form through the same basic collapse mechanism? The answer is not simply that the field is powerful, though it is the most powerful magnetic field confirmed to exist anywhere in the observable cosmos. The answer is that at magnetar field strengths, the magnetic field begins to alter the basic rules under which matter, radiation, and empty space themselves operate. The field does not just push and pull on charged particles the way an ordinary magnet does. It does not merely deflect compass needles or erase credit cards, those familiar effects magnified to astronomical scale. At magnetar intensities, the magnetic field enters a regime where quantum mechanics and electrodynamics collide head-on, where the energy stored in the magnetic field rivals the rest mass energy of fundamental particles like electrons, where the vacuum of space itself ceases to be truly empty and becomes a medium with measurable, direction-dependent physical properties. The field distorts atoms into shapes that should not exist. It alters the way light travels through nothingness. It makes the void itself behave like a crystal. That is where the true violence of magnetars lives, not in the explosions, not in the flares, but in the field itself, a field so extreme that it rewrites the physics of everything it touches. What comes next is the story of that field, the regime it creates, and the impossible things it does to the fabric of reality. The magnetic field around a refrigerator magnet measures roughly 100 Gauss, You can feel it tug on a paperclip from an inch away. It is strong enough to pin a photograph to a metal door, but too weak to affect anything that is not ferromagnetic. You walk through it without noticing. Your body does not respond to it. The atoms in your skin do not change shape. Light passes through it completely unaffected. A refrigerator magnet is, by any meaningful physical standard, harmless. The magnetic field inside a clinical MRI scanner measures roughly 30,000 Gauss, or 3 Tesla. This field is powerful enough to align the hydrogen nuclei in your body, which is how the machine produces images of your internal organs. It is also powerful enough to turn a loose oxygen tank into a lethal projectile, accelerating it across the room at high speed toward the scanner bore. Hospitals enforce strict safety protocols around MRI machines, because even at 30,000 Gauss, a magnetic field becomes dangerous to humans in indirect ways. The field itself does not harm you directly. It harms you by hurling metal objects in your direction. The atoms in your body remain structurally intact. Light still travels normally through the field. The fundamental physics of matter and radiation is entirely unchanged. The strongest continuous magnetic field ever produced in a human laboratory measures roughly 45 Tesla, or 450,000 Gauss. This is the output of specialized research magnets cooled to near absolute zero and consuming enormous amounts of electrical power. In pulsed mode, laboratories have briefly achieved fields exceeding 1200 Tesla, but only for fractions of a second, and only in tiny volumes. These are the absolute limits of human magnetic technology. The most powerful magnetic fields our species has ever created, the culmination of decades of materials, science, and engineering, represent the boundary of what terrestrial physics can sustain. A magnetar's surface field measures roughly 10 billion to 100 billion Tesla. Written in Gauss, that is 100 trillion to 1 quadrillion Gauss. Take the most powerful continuous magnet humanity has ever built and multiply its output by a factor of roughly 1 billion. That is the field strength at the surface of a magnetar, not in some exotic interior region, not in a theoretical maximum that exists only in equations. At the surface, the exterior, the weakest part. To make this number feel real, consider a thought experiment. A magnetar's field could erase every credit card, wipe every hard drive, and destroy every magnetic storage device on the surface of Earth from a distance of roughly halfway to the moon. Not by sending a beam, simply by existing. The ambient field at that distance would still exceed the threshold needed to corrupt magnetic media. That is the fringe of the magnetar's influence, the diluted outer edge of a field that grows enormously more intense as you approach the surface. The interior field is believed to be even stronger, potentially reaching 10 to 100 times the surface value, possibly exceeding 10 to the 16 Gauss in the deepest regions of the star. At those intensities, the magnetic field is no longer simply a force that pushes on charged particles and deflects compass needles at extraordinary strength. It becomes something qualitatively different. It enters a regime of physics where the field itself begins to alter the fundamental behavior of matter, radiation, and the vacuum of space. This regime has a name. Physicists call it the quantum critical threshold, and crossing it changes everything about the way the universe works in the immediate vicinity of the object. The quantum critical magnetic field strength, sometimes called the Schwinger limit for electrons, is approximately 4.4 times 10 to the 13 Gauss. This is the field strength at which the energy associated with the magnetic interaction of an electron equals the electron's own rest mass energy. Below this threshold, magnetic fields affect charged particles in familiar ways. They curve trajectories, they induce currents, they exert forces proportional to charge and velocity. These are the effects you learnt about in a physics classroom. Above this threshold, the magnetic field begins to fundamentally alter the quantum mechanical structure of the particles themselves. The electron's behavior is no longer a small perturbation on top of its normal properties. The magnetic field becomes the dominant feature of the electron's existence. And since electrons are the particles responsible for essentially all of chemistry, all of material structure, and most of the ways light interacts with matter, crossing the quantum critical threshold means entering a world where the basic rules of atomic physics no longer apply in any recognizable form. Magnetar surface fields routinely exceed the quantum critical threshold by factors of 10 to 100. Their interior fields may exceed it by factors of 1,000 or more. Every magnetar that has ever been observed operates deep within this regime. They are not borderline cases. They are not hovering near the threshold. They live far beyond it, in a territory of physics that exists nowhere else in the observable universe except in the immediate vicinity of these objects. Here is what that means for atoms. In everyday conditions, atoms are roughly spherical. An electron orbits the nucleus in a fuzzy probability cloud that extends equally in all directions. The shape is determined by the balance between the electron's kinetic energy and the electrical attraction from the nucleus. This spherical geometry is the foundation of all chemistry. Molecular bonds form because spherical electron clouds overlap and share charge. Crystal structures emerge because spherical atoms pack together in regular patterns. Every material you have ever touched, every substance you have ever breathed, every molecule in your body exists because atoms are round. In a magnetic field above the quantum critical threshold, atoms stop being round. The magnetic field forces electrons into quantized orbits called Landau levels, constraining their motion perpendicular to the field direction into tight, discrete circular paths. The stronger the field, the tighter these orbits become. At magnetar field strengths, the lowest Landau level confines the electron's transverse motion to a radius smaller than the size of an atomic nucleus. The electron can still move freely along the direction of the magnetic field, but in every perpendicular direction, it is locked into an orbit so tight that the atom's shape is completely restructured. The formerly spherical electron cloud collapses into a long, thin needle aligned with the magnetic field. Atoms become elongated cylinders hundreds of times longer than they are wide. This is not a metaphor. This is a confirmed prediction of quantum electrodynamics in strong magnetic fields, verified through decades of theoretical calculation and supported by observations of X-ray spectra from neutron star surfaces. In the vicinity of a magnetar, hydrogen atoms, the simplest atoms in nature, become thin filaments roughly 200 times narrower than their normal diameter. Heavier atoms undergo even more dramatic distortion. The chemistry that governs every interaction in ordinary matter simply ceases to function. Molecular bonds cannot form in their usual configurations because the electron clouds no longer have the shapes required for normal chemical bonding. Instead, atoms can chain together along the magnetic field direction, forming exotic polymer-like structures that have no equivalent anywhere else in nature. The material at a magnetar's surface is not made of any substance that exists in a chemistry textbook. It is a fundamentally alien state of matter, shaped entirely by the magnetic field, with properties that depend on the direction you look at it. This directional dependence is critical. In normal space, the properties of matter are isotropic, meaning they are the same in every direction. A block of iron has the same strength, the same conductivity, the same optical properties regardless of which way you orient it. Near a magnetar, nothing is isotropic. Every physical property depends on the angle relative to the magnetic field. The material is stronger in one direction than another. Light travels at different speeds depending on its polarization. Even the effective mass of an electron changes depending on whether it is moving along the field lines or across them. The magnetic field imposes a preferred direction on everything, turning the space around the magnetar into something more like a crystal than a vacuum. And that brings us to what is perhaps the most disturbing effect of all. The field does not just alter matter, it alters empty space itself. In classical physics, a vacuum is nothing. It is the absence of everything. Light travels through it at a constant speed regardless of direction or polarization. There are no material properties to measure because there is no material. The vacuum is perfectly transparent, perfectly uniform, and perfectly boring. Quantum physics tells a different story. The vacuum is not truly empty. It seethes with virtual particle pairs, electrons and positrons that pop into existence and annihilate each other in timescales so short that they cannot be directly observed. Under normal conditions, these virtual pairs have no measurable effect on light or matter. They exist as a background hum, a quantum noise floor that averages out to zero effect in every direction. But in a magnetic field above the quantum critical threshold, the virtual electron-positron pairs are affected by the field before they annihilate. The field aligns them, stretches them, and alters their brief interactions with passing photons. The result is that the vacuum itself develops different optical properties in different directions. Light polarized parallel to the magnetic field travels at a slightly different speed than light polarized perpendicular to it. The vacuum becomes birefringent, a term borrowed from crystallography that describes a material where light splits into two beams depending on its polarization. Certain crystals like calcite and Iceland spar exhibit this property naturally. You can place a piece of calcite on a page of printed text and see double images of each letter because the crystal splits the incoming light into two polarization-dependent paths. The empty space surrounding a magnetar does the same thing, not because it contains a crystal, because the magnetic field has turned the vacuum itself into one. Vacuum birefringence was predicted by quantum electrodynamics in the 1930s, but for decades it remained purely theoretical because no laboratory magnetic field is remotely strong enough to produce a measurable effect. The quantum vacuum is extraordinarily stiff. Distorting its optical properties requires magnetic fields far beyond anything found in ordinary stellar environments. It was not until astronomers began studying polarized X-ray emission from neutron star surfaces that the effect could finally be tested against observation. Studies of magnetar X-ray emission have provided increasingly strong evidence that vacuum birefringence is real and measurable. Exactly as quantum electrodynamics predicted nearly a century ago, the empty space around a magnetar is not empty in any meaningful sense. It is a magnetically structured optical medium with direction-dependent properties that alter how light propagates, how photons interact, and how radiation escapes from the star's surface. There is an even stranger consequence. In sufficiently strong magnetic fields, a single photon can spontaneously split into two lower energy photons. This process, called photon splitting, is forbidden in a vacuum under normal conditions because it violates conservation of energy and momentum simultaneously. But in a magnetic field above the quantum critical threshold, the field itself can absorb the extra momentum, enabling the split. A gamma-ray photon traveling through the magnetosphere of a magnetar can divide itself into two X-ray photons without encountering any matter at all. The magnetic field acts as an invisible catalyst for a reaction that cannot occur anywhere else in the universe. This process has been theoretically predicted and is believed to play an important role in shaping the observed X-ray spectra of magnetars, softening the highest energy radiation through repeated splitting events as photons travel outward through the intense field. These are not speculative phenomena. Vacuum birefringence, photon splitting, Landau quantization of electron orbits, atomic elongation into needle structures, all of these are established predictions of quantum electrodynamics, the most precisely tested theory in all of physics. The same mathematical framework that predicts the magnetic moment of the electron to 12 decimal places of agreement with experiment also predicts these exotic effects when the magnetic field exceeds the quantum critical threshold. The theory is not uncertain. The effects are not hypothetical. They are the confirmed consequences of known physics applied to field strengths that happen to exist only in one kind of astrophysical object. Magnetars are natural laboratories for extreme quantum electrodynamics, the only places in the observable universe where these effects occur at scales large enough to produce detectable signatures. But the field does not just alter the quantum behavior of particles and empty space, it also attacks the star itself. The magnetic field of a magnetar is not floating above the surface like an invisible cloud. It is anchored in the neutron star's crust, threaded through the crystalline lattice of exotic nuclear material that forms the star's rigid outer shell. The field lines penetrate the crust, winding through it, locked into the lattice structure the way iron filings embed themselves in a block of magnetized steel. This coupling between the field and the crust is absolute. When the field moves, the crust feels it. When the crust shifts, the field responds. And the field is always moving. It never rests. It never reaches a stable final configuration. Deep inside the magnetar, the magnetic field evolves continuously over time. The field configuration is not static. It cannot be, because the conditions inside the star are not in equilibrium. Internal currents redistribute magnetic energy from one region to another. The field twists, winding tighter in some regions while relaxing in others, It decays through a process called ambipolar diffusion, where the magnetic force drives relative motion between the dominant population of uncharged neutrons and the small minority of charged protons and electrons in the core. This diffusion is slow by human standards, unfolding over years, decades, and centuries, but it is relentless on astrophysical timescales. Over time, the internal field reconfigures itself substantially, and as it does, it exerts changing forces on the rigid crust above. The field pushes the crust in new directions. It twists regions that were previously untwisted. It loads stress onto sections of the lattice that had been relaxed. The crust has no choice but to absorb these forces because it is physically locked to the field. The crust resists. It is, after all, the strongest solid material in the known universe. The crystalline lattice of neutron-rich nuclei at the magnetar's surface can withstand shearing forces billions of times greater than the strongest terrestrial steel, billions of times greater than diamond, billions of times greater than any material that human engineering has ever produced or conceived of producing. Under almost any other circumstances in the universe, this material would be completely indestructible. No impact, no explosion, no mechanical force encountered in ordinary astrophysics could fracture it. But the magnetic field of a magnetar is not ordinary astrophysics. At magnetar intensities, the magnetic energy stored in the field per unit volume exceeds the elastic energy the crust can sustain. The field is stronger than the strongest material. The immovable object has met a force that is not merely irresistible, but continuously, persistently, endlessly applied. The field pushes, the crust holds, the stress accumulates. Days pass, weeks, sometimes months or years. The mismatch between the evolving internal field and the rigid external crust grows continuously, like tectonic stress building along a fault line on Earth, except that the forces involved are not geological, they are magnetic, and they are millions of times more intense than anything Earth's geology has ever produced. When the accumulated stress finally exceeds the crust's breaking point, it fractures. The starquake is sudden, catastrophic, and energetically extreme. The crust does not bend or flex gradually. It snaps. The lattice shatters along a fracture zone that can span kilometers of the star's surface. The fracture releases the stored elastic energy in a burst so violent that it launches seismic waves through the neutron star's interior, waves that travel at a significant fraction of the speed of light through the ultra-dense material. Simultaneously, the fracture shakes the magnetic field anchored in the crust. The field lines, suddenly freed from the constraint of the broken lattice, snap into new configurations. Magnetic reconnection events cascade through the magnetosphere, converting stored magnetic energy into radiation. Plasma erupts from the fracture site. Temperatures at the crack soar to billions of degrees. The entire event, from fracture to fireball, unfolds in milliseconds. The result is an X-ray burst, a sudden flash of high-energy radiation emitted from the magnetar's surface and magnetosphere. These bursts are what originally led to the discovery of magnetars as a class of objects. Before anyone understood the underlying mechanism, astronomers detected repeating bursts of soft gamma radiation from specific locations in the sky. The sources would flare unpredictably, emit a cluster of bursts over days or weeks, then fall silent for months or years before reactivating. The objects were classified as soft gamma repeaters, a name that described the observed behavior without explaining the physics. It was only after Duncan and Thomson proposed the magnetar model in 1992, and subsequent observations confirmed the extreme magnetic field strengths through spin-down measurements, that the connection between the bursts and starquakes became clear. The burst activity of a magnetar follows statistical patterns that are eerily similar to earthquake activity on Earth. The distribution of burst energies follows a power law, meaning many small bursts and progressively fewer large ones, exactly the same pattern that describes the distribution of earthquake magnitudes. The waiting times between bursts are correlated, with clusters of activity followed by quiet intervals matching the temporal patterns of aftershock sequences on our own planet. These statistical similarities are not coincidental. They arise because both phenomena involve the same fundamental physics: the sudden release of stress accumulated in a rigid material over time. Earthquake faults store gravitational and tectonic stress. Magnetar crusts store magnetic stress. Both rupture when the stress exceeds the material's breaking point, and both produce cascading failures that follow the same mathematical distributions. Seismologists and magnetar physicists use the same statistical tools to analyze their data, applied to phenomena separated by 15 orders of magnitude in energy scale. During active phases, a magnetar can produce hundreds or even thousands of bursts in a matter of weeks. The activity arrives in clusters, with periods of intense bursting followed by intervals of quiet that can last years. Predicting when a magnetar will become active is currently impossible. The triggers appear to depend on the internal evolution of the magnetic field, a process hidden beneath the opaque surface of the neutron star and inaccessible to direct observation. Scientists can only watch and wait. When the bursts come, they come fast. In 2020, a magnetar called SGRJ 1935 plus 2154 entered one of these active episodes. This particular magnetar, located roughly 30,000 light-years from Earth within the Milky Way, had been known to astronomers for several years as a moderately active soft gamma repeater. Its spin period and spin-down rate indicated a surface magnetic field consistent with the magnetar classification. What nobody expected was that during this particular active phase, the magnetar would do something that transformed an entirely separate field of astrophysics overnight. On April 28, 2020, SGRJ 1935 plus 2154 simultaneously emitted a bright X-ray burst and a millisecond duration radio pulse of extraordinary intensity. The radio pulse was so bright that it was independently detected by multiple radio observatories across the continent, including the Canadian Hydrogen Intensity Mapping Experiment and a dedicated fast transient survey array in the southwestern United States. The radio signal carried energy roughly 40 times less than the weakest fast radio burst ever detected from outside our galaxy, but it was unmistakably similar in its properties. The pulse duration, the spectral characteristics, the dispersion pattern all matched the profile of the mysterious extragalactic fast radio bursts that had baffled astronomers since their discovery in 2007. Fast radio bursts had been one of the deepest unsolved puzzles in modern astrophysics for over a decade. These signals are brief, intense flashes of radio emission arriving from cosmological distances, each lasting only milliseconds, but carrying more energy in radio wavelengths than the Sun produces in an entire day. Hundreds of fast radio bursts had been detected, some repeated from the same source, proving they were not one-time cataclysmic events. Multiple theoretical models had been proposed to explain their origin. Most of them invoked magnetars in some form, either through giant flares, through starquake-driven magnetospheric events, or through interactions between a magnetar and its surrounding environment. But no direct observational link between a known magnetar and a fast radio burst had ever been established. Theory pointed toward magnetars. Proof was missing. The April 2020 event from SGRJ 1935 plus 2154 provided that link. A magnetar in our own galaxy, during a routine starquake-driven burst, had produced a radio signal powerful enough that if the same event had occurred in a nearby galaxy, it would have been detected as a fast radio burst by our instruments. The observation did not prove that all fast radio bursts come from magnetars. The energy gap between the galactic event and the brightest extragalactic bursts spans several orders of magnitude, suggesting that the most powerful fast radio bursts may require more extreme conditions than a typical magnetar burst. But it established, for the first time, a confirmed physical connection between magnetar activity and one of the most energetic classes of radio transients in the cosmos. Magnetars were not just cracking their own surfaces and releasing X-ray bursts. They were, under the right conditions, producing signals detectable across hundreds of millions of light-years. This is what makes the magnetic field of a magnetar qualitatively different from any other magnetic field in the universe. An ordinary magnetic field is a force. It pushes, it pulls, it deflects, it induces. Those are mechanical effects, powerful but conceptually simple. A magnetar's field does all of those things, but it also does something no other magnetic field can do. It enters the quantum critical regime, and begins altering the fundamental behavior of matter and energy at the particle level. It reshapes atoms. It restructures the vacuum. It splits photons. It breaks the crust of the densest solid material in existence. It drives seismic activity on a dead star that statistically resembles earthquake sequences on a living planet. And it produces radio signals bright enough to be detected from other galaxies. The field is not merely strong, it is structurally violent. It is an active, persistent, evolving agent of physical change, operating continuously on the star, its immediate environment, the quantum structure of the vacuum, and the space surrounding it for thousands of light years in every direction. It does not sit passively around the magnetar like a magnetic halo waiting to be measured. It interacts with every component of the system at every moment. It stresses the crust until the crust breaks. It shapes the magnetosphere into a dynamic, energetic plasma environment. It alters the quantum properties of the vacuum in ways that change how light propagates. It converts stored magnetic energy into radiation through mechanisms that have no parallel anywhere else in the observable universe. And through the fast radio burst connection, it reaches across cosmological distances to announce its violence to instruments on other worlds. Everything about a magnetar's magnetic field operates in a regime that is qualitatively different from any other magnetic environment in nature. Planetary magnetic fields are passive shields. Stellar magnetic fields are modest accessories. Even the fields of ordinary neutron stars and pulsars, as impressive as they are, operate below the quantum critical threshold and affect their surroundings through familiar electromagnetic interactions. Only magnetars cross the line. Only magnetars enter the regime where the field alters the structure of atoms, the properties of the vacuum, and the behavior of photons in ways that rewrite the local rules of physics entirely. And yet, everything described so far represents only the chronic, ongoing baseline violence of a magnetar's existence. The star quakes, the X-ray bursts, the crust fractures, the field reconnection events, the fast radio pulses, these are the routine weather of a magnetar's daily life. They are what happens between the truly catastrophic episodes. The giant flares described at the beginning of this story, the events that release more energy in a fraction of a second than the sun produces in hundreds of thousands of years, are something else entirely. They represent the extreme upper tail of the magnetar's violence distribution, the rare moments when the entire magnetic architecture of the star undergoes catastrophic global failure simultaneously. And the consequences of those events, from relativistic fireballs to the nuclear synthesis of heavy elements to the production of blast waves that reshape the surrounding interstellar medium for light years in every direction, reveal a depth of physical hostility that goes far beyond anything the routine bursts suggest. What comes next is the full accounting of that violence, the complete catalogue of what magnetars do to the universe around them, and the final reckoning with what it means that stellar death can produce something this relentlessly, structurally, fundamentally extreme. Imagine a hierarchy of violence. At the bottom, you have routine magnetar behavior. Small X-ray bursts, each one lasting anywhere from a few milliseconds to a few seconds, each one releasing energy equivalent to what our sun produces over the course of a year or so. These are the minor tremors, the everyday seismic activity of a crust under perpetual magnetic stress. They arrive in clusters, sometimes dozens per day during an active episode, sometimes nothing at all for months or years at a stretch. Each individual burst represents a localized fracture event, a small section of the crystalline lattice giving way under accumulated magnetic force, snapping and releasing its stored elastic energy as a sharp flash of X-ray radiation that fades almost as quickly as it appears. By any terrestrial standard, these routine bursts are cataclysmic. A single one carries more energy than any volcanic eruption, any earthquake, any impact event in Earth's recorded geological history. If you could somehow detonate the energy of a single routine magnetar burst on Earth's surface, the result would dwarf any weapon humanity has ever built. But by magnetar standards, these bursts are background noise. They are the hum of a machine that never fully powers down, the sound of a crust that is always under stress, always approaching failure somewhere along its surface, always releasing small packets of energy as the magnetic field slowly, relentlessly rearranges the structure beneath it. Above the routine bursts sit the intermediate flares. These are rarer, perhaps a few per decade from any given magnetar, and they release energy roughly 1,000 to 10,000 times greater than the ordinary bursts. An intermediate flare involves not a single localized fracture but a larger-scale rearrangement of the crust and the magnetic field above it. Multiple fracture zones may activate simultaneously. The magnetic reconnection events cascade through a larger volume of the magnetosphere. The X-ray emission is brighter, harder in spectrum, and longer in duration. Intermediate flares are powerful enough to trigger detectable responses in spacecraft instruments across the solar system. Though they do not typically saturate those instruments the way giant flares do, they occupy a middle ground, too energetic to be dismissed as routine, too common to be treated as singular catastrophes. They are the severe storms of the magnetar world, destructive and dramatic but not yet apocalyptic. And then, at the very top, far above everything else, sit the giant flares. These are the events that define magnetar violence for anyone who encounters the subject for the first time. They occur perhaps once or twice during a magnetar's entire active lifetime. Some magnetars may never produce one at all. When they happen, they represent a catastrophic global failure of the magnetic field configuration. Not a localized crack, not a regional rearrangement. A wholesale restructuring of the entire magnetic architecture of the star, releasing energy that exceeds the routine bursts by factors of 1,000,000 or more. The three confirmed giant flares in observational history, from SGR-05 26-66 in 1979, from SGR 1900 plus 14 in 1998, and from SGR 1806 minus 20 in 2004, represent the only direct observations humanity possesses of this phenomenon. 3 events in nearly 50 years of gamma-ray astronomy. The sample is tiny, the physics is extreme, and each event revealed new aspects of magnetar violence that pushed the boundaries of what theorists believed was possible. But the giant flares are not just flashes of gamma radiation that blind instruments and fade. They have consequences that persist for weeks, months, and years after the initial burst. The December 2004 flare from SGR 1806-20 produced a relativistic blast wave, a shell of magnetized plasma expanding outward from the magnetar at a significant fraction of the speed of light. Radio telescopes detected the expanding blast wave approximately 7 days after the flare, and they tracked its evolution for weeks as it ploughed into the surrounding interstellar medium. The radio afterglow was roughly 500 times brighter than the afterglow from the previous giant flare observed from SGR 1900+14. It behaved almost identically to the afterglows of cosmological gamma-ray bursts, the brilliant explosions associated with the deaths of the most massive stars and the mergers of compact objects at the edges of the observable universe. The same physics that governs the most energetic explosions in the cosmos was at work in the aftermath of a single magnetar's starquake. That afterglow is profoundly important because it demonstrates that magnetar violence does not remain confined to the star and its immediate magnetosphere. It reaches outward, it propagates, it changes things. The blast wave sweeps up interstellar gas and dust, heating it, compressing it, and accelerating charged particles to enormous energies. The expanding shell of debris reshapes the local interstellar environment for light years around the magnetar, sweeping up ambient gas and dust, and compressing it into dense shells that glow faintly in radio wavelengths for years after the initial flare has faded. Over time, this material disperses and merges with the broader interstellar medium, carrying the chemical and energetic signature of the flare into the galaxy at large. Magnetars are not isolated points of violence. They are engines that inject energy, particles, and matter into their galactic neighborhoods. Some magnetars are surrounded by structures called magnetar wind nebulae, clouds of energetic particles and magnetic fields that have been expelled from the star over the course of its active lifetime. These nebulae are powered by the continuous outflow of relativistic particles from the magnetar's magnetosphere, a wind of electrons and positrons accelerated to near light speed by the star's immense rotating magnetic field. The wind inflates a bubble in the surrounding interstellar space, creating a visible structure that can be detected in radio and X-ray wavelengths extending across light years. These nebulae provide evidence that the magnetar's violence extends far beyond individual burst events. Even between bursts, even during quiet periods, the magnetar is continuously pumping energy into its surroundings. The wind never stops. The field never rests. The star radiates hostility as a baseline condition of its existence. But the discovery that truly reframed the meaning of magnetar violence came in 2025. Earlier in this story, we introduced the finding. Here is what it means. When the crust of SGR 1806-20 fractured during the December 2004 giant flare, the violence did not just release energy in the form of radiation and plasma, it physically ejected material from the neutron star's surface. Fragments of the shattered crust, composed of neutron-rich nuclear matter unlike anything found elsewhere in the universe, were launched outward at roughly 10% the speed of light. That material, torn from the densest solid in nature and flung into space by magnetic forces beyond comprehension, then underwent one of the most remarkable nuclear processes known to physics. As the ejected debris expanded and cooled, conditions within it briefly matched the extreme requirements for the rapid neutron capture process, the R process. Neutrons from the crustal material bombarded seed nuclei at a furious rate, building progressively heavier elements through a cascade of captures and radioactive decays. The process climbed the periodic table in seconds, assembling atomic nuclei with masses far beyond iron, beyond tin, beyond the lanthanides, reaching elements like gold, platinum, and uranium. These are among the heaviest stable and near-stable elements in nature, and they were being forged not in the collision of two neutron stars spiraling together over millions of years, but in the debris of a single starquake on a single dead star. The evidence was written in the delayed gamma-ray light curve that followed the flare. What matters now is what that evidence quantified. The total mass of freshly synthesized heavy elements produced in the December 2004 event was approximately 1/1,000,000th of a solar mass. That quantity sounds small until you realize it is equivalent to roughly 1/3 of our entire Earth's mass worth of gold, platinum, and other heavy elements assembled from nuclear debris in a single event lasting less than a second. This discovery carried implications that extend far beyond the magnetar itself. Neutron star mergers were, until 2025, the only confirmed astrophysical site of reprocessed nucleosynthesis. The merger detected through gravitational waves in 2017 had produced clear evidence of heavy element synthesis, establishing neutron star collisions as a source of the universe's gold, platinum, and uranium. But neutron star mergers are rare. They require two neutron stars to spiral together over billions of years before finally colliding. The delay between the formation of the neutron stars and their eventual merger is enormous, typically billions of years. This creates a problem for the early universe. The most ancient stars in our galaxy, those formed in the first few 100 million years after the Big Bang, already contain trace amounts of R process elements. These elements had to come from somewhere, and neutron star mergers could not have produced them because there had not been enough time for any neutron star binary to complete its inspiral. Magnetars solve this problem elegantly. They are born immediately after a massive star dies. The delay between star formation and magnetar creation is merely millions of years, the lifetime of the progenitor star. That is a negligible interval on cosmic timescales. If magnetar giant flares can forge reprocess elements, as the 2025 discovery confirms, then the earliest magnetars in the universe, born from the first generation of massive stars to form after the Big Bang, could have seeded the primordial interstellar medium with heavy elements long before any neutron star merger had time to occur. The gold and platinum detected in the oldest, most metal-poor stars in our galactic halo, stars that formed when the universe was young, and neutron star mergers had not yet had time to contribute, may not have come from collisions at all. They may have come from starquakes on magnetars that lived and died within the first few 100 million years of cosmic history. The researchers who made the discovery were careful to note that magnetar giant flares are likely not the dominant source of R process elements in the galaxy overall. Neutron star mergers, though rarer, produce far more R process material per event, but magnetars occupy a unique niche. They operate with a short delay time after star formation. They can contribute to chemical enrichment at epochs, where mergers cannot. And their contribution, while modest per event, accumulates across the many magnetars the galaxy has produced over its lifetime. The total reprocess yield from all magnetar giant flares across the Milky Way's history may account for a meaningful fraction of the galaxy's heavy element budget, perhaps up to 10% according to preliminary estimates, though this figure remains uncertain. This reframes what magnetar violence means on a galactic scale. These objects are not just extreme curiosities producing spectacular but isolated events. They are contributors to the chemical evolution of the galaxy. Their violence produces matter. Their destruction creates elements that eventually find their way into molecular clouds, into protoplanetary disks, into the rocky bodies that form around new stars. Some fraction of the heavy elements in our own solar system, in the Earth's crust, in the circuitry of the device you are using to hear this story, may trace its origin to a magnetar that cracked its own surface billions of years ago and scattered the products of that violence into interstellar space. The chain from stellar death to magnetar formation to starquake to element synthesis to planetary incorporation to human technology is long, but every link in it is physically real and observationally supported. This is where the comparison with black holes becomes most revealing. Black holes are often presented as the ultimate extreme objects in the universe. They are more massive than magnetars. Their gravitational fields are stronger. They bend space-time so severely that nothing, not even light, can escape from within their event horizons. In popular culture, black holes represent the final word in cosmic violence and extremity. If you ask most people to name the most terrifying object in the universe, they would say a black hole. But here is what black holes actually do. They sit there, quietly, behind an event horizon that hides everything about their interior from the rest of the universe. A black hole does not emit light. It does not produce X-ray bursts from its surface, because it has no surface. It does not crack or fracture, because there is no solid structure to break. It does not produce magnetic flares, because whatever magnetic field it carries is trapped behind the horizon. It does not forge elements, because no nuclear processes occur at the event horizon boundary. A black hole is gravitationally extreme. It is mathematically fascinating. But in terms of active, ongoing physical violence done to the surrounding universe, a black hole is remarkably passive. It pulls things in. It does not push things out. Its violence is the violence of consumption, of erasure, of ending. A magnetar is the opposite in almost every way that matters for the question of violence. It has a surface, a real, physical, exposed surface made of the most extreme solid material in the universe, and that surface is not hidden behind any horizon. It is right there, accessible to observation, radiating information about its state into space for anyone with the right instruments to measure. The magnetar emits radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. It fractures and rebuilds its crust in cycles of destruction and recovery. It launches plasma and particles into space at relativistic velocities that produce detectable afterglows. It forges new atomic nuclei from its own shattered body. It produces magnetic fields that alter the quantum structure of the vacuum in measurable ways. It sends signals through fast radio bursts and gamma-ray flares that are detectable from other galaxies entirely. Everything a magnetar does, it does in the open, without an event horizon to hide behind, without a veil of gravitational silence to absorb its activity. Its violence is not the quiet inward consumption of a black hole. It is the active, outward, ongoing, structural hostility of an object that refuses to be inert despite being a corpse. That is the distinction that earns magnetars the title of most violent objects in the universe. Not most massive, not most gravitationally extreme, most violent. Violence implies action. It implies force applied to something. It implies consequences that propagate outward. By every one of those measures, magnetars exceed black holes. They do more to the universe around them per unit of time, per unit of mass, and per unit of volume than any other confirmed astrophysical object. They are the most actively hostile things that exist, and they are temporary. That is perhaps the most unsettling part of the entire story. Magnetars do not last. The extreme magnetic field that defines a magnetar decays over time. The same internal processes that drive the starquakes and flares, the ambipolar diffusion, the Hall drift, the ohmic dissipation of currents in the crust, all of these mechanisms drain energy from the magnetic field. The field weakens. The starquakes become less frequent, the bursts become less energetic, the magnetar dims. Over a period of roughly 10,000 years, the magnetic field decays below the threshold where extreme behavior occurs, and the former magnetar becomes an ordinary, quiet, slowly spinning neutron star, indistinguishable from the billions of others scattered through the galaxy. The violence stops, the object persists, but its identity as a magnetar ends. 10,000 years. That is the active window. 10,000 years out of a neutron star lifetime that can stretch for tens of billions of years. It is like a human being who lives for 80 years but spends only the first 40 minutes in a state of extraordinary capability before settling permanently into quiet normalcy. It means that at any given moment, only a tiny fraction of all the neutron stars in the galaxy are actively behaving as magnetars. The roughly 30 confirmed magnetars we observe in the Milky Way represent only the ones currently in their violent phase. For every active magnetar we see today, there are thousands, perhaps tens of thousands, of former magnetars that have already burned through their magnetic energy and settled into permanent retirement. The galaxy is littered with the invisible husks of dead magnetars, objects that once cracked their own surfaces and forged gold from their wounds, but now spin silently in the dark, carrying no external trace of the extraordinary violence they once produced. This transience makes the magnetar phenomenon feel almost tragic in a way that other astrophysical extremes do not. The universe builds these extraordinarily extreme objects through a process that takes millions of years of stellar evolution and ends in a gravitational collapse lasting milliseconds. The result is the most violently active remnant in the cosmos. And then, in a cosmically insignificant window of 10,000 years, the violence dissipates. The object that was once capable of ionizing a planet's atmosphere from across the galaxy becomes just another faint point source in an X-ray survey, unremarkable and unnoticed. The fire burns out. The magnetar goes gentle. But here is the final truth that this story has been building toward. The truth that sits beneath every fact and every measurement and every comparison in everything we have explored so far. And it is this: magnetars are not anomalies. They are not glitches in the stellar life cycle. They are not freak accidents produced by unlikely conditions. They are a natural, predicted, and routinely produced outcome of the death of massive stars. Approximately 1 in 10 core collapse supernovae creates a magnetar. The universe manufactures them as a standard byproduct of stellar evolution. Every galaxy with active star formation is producing magnetars right now. They are being born in the Milky Way. They are being born in Andromeda. They are being born in galaxies so distant that their light has been traveling for billions of years. The process is ordinary, the result is extraordinary, and the result is this: some stars die, and the thing they leave behind is more violent than they ever were while alive. A massive star burns for millions of years, fusing elements, radiating light, holding itself up against gravity through the steady output of nuclear energy. It is powerful, luminous, and stable. Then it runs out of fuel, its core collapses, a supernova blasts its outer layers into space. And what remains, the tiny, ultra-dense, magnetically extreme remnant left behind in the debris, is not a quiet memorial to the star that was. It is something more hostile than the star ever managed to be during its entire burning lifetime. The star could not warp the vacuum of space. The magnetar can. The star could not crack its own surface. The magnetar does, routinely. The star could not forge gold from its own body. The magnetar can. In a single starquake, the star could not produce signals visible from other galaxies in a fraction of a second. The magnetar did. On December 27th, 2004, death did not make this object quiet. Death did not produce a memorial. Death did not leave behind something diminished, something fading, something winding down toward a final rest. Death made it worse. That is the sentence that should sit with you long after this story ends, because it violates everything human intuition expects about endings. In every domain of human experience, death is the cessation of activity. Things stop, energy dissipates, structures decay. What remains after death is always less than what existed before. The dead do not rise to become more powerful than they were in life. Entropy wins, complexity decreases. The arrow points one way, but in the physics of extreme stellar remnants, that is exactly what happens. The collapse of a massive star's core produces an object so compressed, so magnetically wound, so structurally extreme, that the remnant's capacity for violence far exceeds anything the parent star could produce. The progenitor star was a fusion engine. The magnetar is a magnetic bomb that detonates repeatedly, recovers and detonates again. The progenitor was powerful. The magnetar is hostile. There is a difference, and it matters. We use the word remnant to describe what a star leaves behind when it dies. The word implies something left over, something diminished. A remnant of a meal is the scraps on the plate. A remnant of a building is the rubble after demolition. The word carries an emotional assumption of reduction, of aftermath, of something less than what came before. Magnetars expose that assumption as false. They are not less than their parent stars. They are more concentrated, more energetic per unit mass, more magnetically extreme, more violently active, more physically hostile to the space and matter around them. Calling a magnetar a remnant is like calling a landmine the remnant of a weapons factory. Technically true, emotionally misleading. The factory was productive. The landmine is dangerous. The factory built things. The landmine exists to destroy. The transition from star to magnetar is not a diminishment. It is a transformation from creation into something that exists at the boundary between survival and catastrophe. There are roughly 30 of them in our galaxy right now. 30 dead stars wrapped in magnetic fields that rewrite the local laws of physics. 30 objects smaller than a city, capable of producing energy bursts visible from other galaxies. 30 remnants that crack their own surfaces, forge heavy elements from their wounds, warp the quantum vacuum, and send relativistic blast waves into the interstellar medium. 30 objects that the universe built through the ordinary process of stellar death, and that turned out to be among the most extreme physical systems that matter can form. They will not last. Within 10,000 years, their fields will decay, and they will go silent. New magnetars will be born in the supernovae of other massive stars, and those too will burn through their violence and fade. The cycle continues in every galaxy, with active star formation, a steady production line of the most hostile objects in nature, each one blazing for a cosmic instant before settling into the long, quiet retirement of an ordinary neutron star. But while they burn, nothing in the universe matches them. Not in magnetic intensity, not in the rate of energy release per unit mass, not in the sheer breadth of physical mechanisms they employ to inflict violence on their surroundings, not in the range of consequences their activity produces, from altered vacuum states to synthesized elements to galactic-scale chemical enrichment. Magnetars are the most violent objects in the universe, not because of one thing they do, but because of everything they do, simultaneously, from inside a dead star barely 20 kilometers across. Some stars die quietly. They shed their outer layers, leave behind a white dwarf, and cool into darkness over billions of years. Some stars die violently but conclusively. They explode as supernovae, scatter their material into space, and leave behind a neutron star or black hole that settles into permanent calm. But some stars, roughly 1 in 10 of the most massive ones, die into magnetars. They die into violence that survives their death. They die into objects that are more dangerous, more extreme, and more physically hostile than the stars that created them ever were. And the word star almost stops feeling useful for describing what they leave behind. What they leave behind is something else. Something the universe builds routinely, but that defies every expectation about what death should produce. The most violent objects in the universe are not the largest. They are not the oldest. They are not the most massive. They are the dead ones. The small, dense, magnetically tortured remnants of stars that should have gone quietly into the dark, but instead became something the cosmos has no gentle name for. They are magnetars, and they are out there, right now, in our galaxy and in billions of others, cracking and flaring and forging and screaming into the void, doing everything the laws of physics allow a dead star to do, which turns out to be far, far more than anyone ever imagined a dead star could.